October 4th, 2021. Just after 11 a.m. Pacific time, something unusual starts appearing in global network monitoring systems. Facebook's address ranges, the blocks of IP addresses that carry traffic to Facebook's servers, are disappearing from the internet's routing tables. Not degrading, not slowing, disappearing. Within minutes, Facebook, Instagram, WhatsApp, and Messenger are all unreachable. Billions of users worldwide try to load these apps and get nothing. But here's the part of the story that most news coverage missed, the part that reveals something genuinely important about how internet infrastructure works. Facebook's own engineers couldn't fix it quickly, not because the problem was technically complex, not because they didn't know what was wrong, but because the tools they needed to fix the problem, the internal systems, the remote access, the configuration management infrastructure, all ran on the same network that had just disappeared. The people trying to repair the outage couldn't reach the systems they needed to repair. Some engineers had to drive to Facebook's data centers physically, to badge in, to sit down at hardware directly. And even then, additional security systems designed to protect against unauthorized access slowed them down further, because those systems too were behaving unexpectedly in the absence of normal network connectivity. 6 hours. One of the most well-resourced technology companies in the world knocked offline for 6 hours, partly because fixing the problem required access to infrastructure that the problem had made inaccessible. To understand how this is possible, we need to talk about what actually happened and what it reveals about the way large-scale internet infrastructure is structured and where its deepest vulnerabilities lie. Let's start with what caused the outage, because it wasn't an attack and it wasn't a hardware failure. It was a routine maintenance operation that went wrong in a specific and instructive way. Facebook's internal network, the infrastructure connecting their data centers, their servers, their internal tools, is enormous. Dozens of data centers on multiple continents, connected by private high-capacity links, forming a private network that sits underneath all their public-facing services. Managing a network this size requires automated tools that can make configuration changes across many routers simultaneously. On October 4th, someone ran a command to audit and update the configuration of Facebook's backbone routers, the high-capacity routers connecting their data centers to each other and to the internet. The command was part of routine maintenance, but it contained an error. Instead of making a targeted configuration change, it effectively told Facebook's backbone routers to withdraw their BGP route announcements, the protocol organizations use to announce their address space to the rest of the internet. Facebook uses BGP to tell the world, these address ranges are ours, send traffic for them our way. When that misconfiguration command executed, Facebook's routers stopped making those announcements. From the global internet's perspective, Facebook's address space ceased to exist. Within minutes, routers around the world began expiring their cached routes to Facebook's addresses. There was nothing to refresh them, no new BGP announcements coming from Facebook's network. The routes aged out. Traffic destined for Facebook had nowhere to go. The service vanished. This is sometimes called a self-inflicted BGP withdrawal, not a hijack, not an external attack, but a network operator accidentally instructing their own infrastructure to stop announcing itself to the internet. But the BGP withdrawal is only half the story. The other half, the part that made recovery so slow, is about something called a dependency loop, and it's where the real architectural lesson lives. Think about what Facebook needs in order to fix a routing problem. They need engineers to access configuration systems. Those systems are servers. The servers are inside Facebook's network. Accessing them remotely requires network connectivity. Network connectivity to Facebook's infrastructure requires Facebook's BGP routes to be active. The BGP routes just disappeared. This is a dependency loop, a circular chain of requirements where fixing problem A requires resource B, but resource B requires problem A to already be fixed. The routing problem took down the access infrastructure needed to fix the routing problem. The very act of having a highly integrated, internally connected infrastructure, which is normally a massive operational advantage, became a trap in this specific failure mode. Facebook isn't unique in this. Any large organization that runs its operational and management infrastructure on the same network as its public services faces this same potential trap. Under normal conditions, this integration is invisible and beneficial. Everything talks to everything efficiently over the same internal network. But when the network itself is the failure, the integration becomes a liability. Every tool that depends on the network disappears along with the network. This is why resilient infrastructure design includes what engineers call out-of-band management, a separate, independent network path to reach critical infrastructure that exists entirely outside the primary network. A management network that doesn't depend on the same BGP routes, the same backbone routers, the same configuration systems, something that stays reachable even when everything else is down. Facebook had some of this. But the scale and speed of the collapse, combined with physical security systems behaving unexpectedly under abnormal network conditions, meant that even out-of-band access was slower than expected. The 6-hour duration wasn't just about the technical fix. It was about the time cost of operating in degraded conditions where the normal tools for fast recovery weren't available. The Facebook outage is dramatic because of its scale. Billions of users, 6 hours, global visibility. But the pattern it represents is not unusual. Large outages that affect many seemingly unrelated things through a single cause are a recurring feature of internet infrastructure, and they tend to follow recognizable shapes. The first shape is what happened to Facebook, a single choke point failure. One component, in this case, the BGP routing infrastructure, sits underneath everything. Every service, every tool, every system depends on it. When it fails, everything depending on it fails simultaneously. Modern internet services are built in layers. DNS sits underneath everything that uses domain names. BGP routing sits underneath everything that uses the internet. Cloud provider networks sit underneath everything hosted on those clouds. When one of these foundational layers fails, the outage doesn't look like one thing breaking. It looks like everything breaking, because everything built on top of that layer breaks simultaneously. This is why, in June 2021, a configuration error at Fastly, a content delivery network most users had never heard of, took down large portions of the web simultaneously. Reddit, Twitch, the New York Times, the UK government website, seemingly unrelated services, all going down at the same moment, all for the same reason. They all sat on top of the same CDN layer, and that layer had a problem. The services weren't related to each other, but they shared infrastructure. And shared infrastructure means shared failure modes. The second shape is cascading failure, where one failure creates conditions that cause secondary failures. Here's how this plays out in routing. Imagine a major link in the internet's backbone fails. Traffic that was flowing through that link has to reroute. The alternative paths exist. Good network design ensures redundancy, but they now carry additional load. If the additional load exceeds their capacity, they start dropping packets. Routing protocols, detecting the packet loss, may interpret it as a sign of further failures, triggering additional route withdrawals, additional reconvergence, additional traffic shifts. Neighboring links now absorb even more traffic, more congestion, more apparent failures. Each step in the cascade looks like a new failure to the routing layer. What started as one link failure has propagated into a much broader disruption. This is sometimes called a storm in networking, a BGP update storm, a route withdrawal storm, where the system's own mechanisms for responding to failure generate so much traffic and recomputation that they degrade performance further. The cure and the disease become tangled together. Good network design tries to limit cascading failure through careful capacity planning. But this requires significant over-provisioning. And in practice, most networks operate with less redundant capacity than a worst-case scenario would ideally require. The third shape is recovery asymmetry. The observation that large routing-based outages often take dramatically longer to recover from than they took to cause. The Facebook outage took minutes to create and hours to resolve. Causing an outage through a routing misconfiguration is fast, because routing propagation is fast. Recovering requires reversing every step of that propagation. The correct routes have to be re-announced. Every router that expired or withdrew the old routes has to receive the new announcements. BGP convergence after a recovery isn't instantaneous. Even after the root cause is fixed, the recovery ripples outward through the same propagation machinery that spread the failure. But physical access requirements, security systems, organizational coordination, and the challenge of diagnosing the exact cause all add time. Facebook's engineers knew fairly quickly what had happened. Getting to a position where they could safely re-announce the routes without risking making things worse required careful work under difficult conditions. The asymmetry between how fast you can break something and how long it takes to fix it is one of the more uncomfortable realities of operating large-scale internet infrastructure. It argues strongly for extremely conservative change management, slow, careful, tested changes rather than fast, automated ones. The Facebook outage happened during what was supposed to be routine maintenance. The word routine is the warning sign in retrospect. So what does all of this tell us about how to think about internet resilience? The internet is genuinely robust against a wide range of failures. It's distributed design, no central authority, routing that adapts around problems, redundant paths between most points, means that most failures stay local. The internet routes around damage, but it routes around damage at the routing layer. Failures at the routing layer itself don't get routed around, they are the routing. When they fail, the internet's self-healing mechanism is the thing that's broken. The Facebook outage, the Fastly outage, the Pakistan Telecom incident from the last video, all of these are failures at or near the routing layer. And in each case, the scale of impact was dramatically larger than the apparent scale of the cause. One misconfigured command, one CDN configuration error, one leaked BGP announcement, each one producing outages affecting hundreds of millions of users. Because the thing that broke was foundational infrastructure that everything else depended on. Understanding this changes how you think about internet reliability. It's not enough to ask, is this service reliable? The question is also, what foundational infrastructure does this service depend on, and what happens if that infrastructure fails? For the internet's routing layer, that question doesn't have a comfortable answer yet. The work of making BGP more secure is ongoing. The work of designing infrastructure that can recover from routing failures without requiring physical access is being done. The work of limiting the blast radius of routing misconfigurations is advancing, but slowly, across thousands of independently operated networks that each make their own decisions. The internet works, reliably and impressively, the vast majority of the time. The moments when it doesn't, the big, dramatic, globally visible failures are almost always stories about the routing layer, about the foundational infrastructure that the rest of the internet is built on top of, and about what happens when that foundation briefly gives way.